Okay.
All right, thank you. I have to admit I will not be using formulas in my talk because it's late in the day. That's always a lie. The real reason is that I don't know how to write formulas in PowerPoint. But I will try. But I will try to explain things that what I mean kind of without them. And if needed, if we would have a blackboard in discussion, I don't think we'll need it in the actual talk. So part of the story will be how quantum electrodynamics will get sort of separated out of quantum mechanics, or the borderline between them was construed. I will be using the talk the three names: quantum electrodynamics, relativistic quantum theory, and quantum field theory, kind of interchangeably. Understanding they're not exact synonyms, but the people who were doing these things back then, they also used this kind of these three terms more or less interchangeably. Some preferred one over the other, with some differences in meaning, but on the whole, they kind of some of them could refer to similar things by the three possible names: quantum electrodynamics, relativistic quantum theory, or quantum field theory. We're starting with 1925, and for the first couple of years after 1925, there was no actual separation between QED and quantum mechanics. It was not yet clear what quantum mechanics will be, and the term was not used. The typical term that was used was the new quantum theory. And people who used this term, they were inspired either by Heisenberg initial paper from 1925 or by Schrödinger initial paper from 1926, and were trying to do whatever they could with kind of this inspiration. And some of the problems they were trying to solve would later be classified as quantum mechanics, and some of the problems they were trying to solve would later be classified as quantum mechanics. But at the beginning, for the first 2 years, it was more or less mixed. And within that mix of sort of a seminal papers on quantum mechanics, yes, we do find kind of a sort of a post factum when we look at them, some of the problems that later would go into relativistic quantum theory. The first one would be indeed Jordan in one of the first papers about which we just heard now, the fluctuations. It's part of the seminal paper quantum mechanics. The one comment I want to say about the paper we just heard is that Jordan's claims notwithstanding, it was perfectly possible to solve the problem in the old quantum theory. Ehrenfest was not the only paper that existed then. There were about a dozen different approaches, some less satisfactory than others, but one could solve the problem of fluctuations with both terms in the old quantum theory too. But Jordan indeed kind of introduces in his part of that Dreimann-Arbeit, the method of the quantization of electromagnetic radiation, electromagnetic waves, and derives the fluctuation formula with both terms. Also in 1926, as part of this mix, there were quite a few people, half a dozen of them, were deriving various relativistic versions of the Schrödinger equation, starting with Schrödinger himself, even though unpublished, some with, some without fifth dimensions, and also with all these papers, including the first Heisenberg's one, were different calculations of the intensities of radiation, which is on the one hand obviously an electromagnetic problem, but also kind of an important concept for quantum mechanics per se. So this situation, when the two things would still be unseparated, lasted until sort of the very end of 1926. And the first paper that actually claimed that there is there will be two different theories is Dirac's seminal paper of the early 1927, actually written at the end of 1926, the quantum theory of the emission and absorption of radiation. And Dirac started with a very explicit claim saying that by now, which is by the end of 26, we have the fairly complete system of quantum dynamics, which would become quantum mechanics and would be called this, ever since then, quantum mechanics. At the same time, he says almost nothing has been done in quantum electrodynamics. And it's clear if you read kind of Dirac's logic, what's his logic, how does he distinguish kind of or at first, what I say, what makes him think that one part of the thing is complete is his and Jordan transformation theory. So he thought that it's November 1926, he and Jordan independently produced thing kind of which at that time was called transformation theory, which in their view, indeed, sort of in some sense defined what can be solved, what cannot be solved, in which representation. And from this point of view, Dirac essentially says that this kind of makes a certain part of the theory complete, and now we can say actually what it does and what it does not. And why Dirac says nothing, very little has been done in quantum dynamics, so what does the theory does not? For Dirac, the most important thing is that this complete part of the quantum theory that is done now is essentially based on Hamiltonian approach. And Hamiltonian approach is non-relativistic by definition because it separates time from space. And from Dirac, which kind of takes these things very seriously, that means that this theory cannot be made relativistic in a fundamentalist thing. And for anything relativistic, something else will be needed. And he proceeds with this paper trying to present the new quantum theory of radiation. He admits that it's not that desired relativistic theory, because it still uses Hamiltonian approach. So for him, it's like a partial step towards something future. But this is what he does in that paper. Interestingly enough, there are three different ways, three different approaches how Dirac quantizes radiation in this paper. First, he starts it with a very, very strange method, which after that would be called second quantization. Dirac doesn't use this term, but that's what he actually does. He does a very strange procedure. He takes a Schrödinger function, psi function, and quantizes it, in some sense, a second time, and without sort of explaining why he does so. But that's what the paper actually starts with. And in my analysis, this is what was the origin of the entire paper. And he shows that if you do this, then you receive the treatment of a quantum system with Bose ensemble of quantum particles. To prove this, he does a second approach. He basically say, okay, let's actually construct the quantum mechanical system with the Bose ensemble and show that it's the same as second quantization, and he does so. And at the last thing, he also said, okay, and another thing to do is to quantize electromagnetic radiation or electromagnetic waves a la Jordan, but he does it with more sophistication, and he achieves more result. And he generally claimed that in some sense all three different ways of doing quantum theory of radiation are roughly the same thing. So they produce very similar results. It's not true in the full sense of the word, because some approaches are more powerful than others. We can solve some problems better with one. But on the whole, he tries to prove that doing each of these three things, you receive the same, roughly the same similar theory of quantum radiation. I will not go too much into the story of second quantization. Maybe just one little remark, because this is where I will skip formula. It is possible to deduce from Dirac's, typically Dirac's papers are supposed to be written in such a way, in such a perfect way, that you will not be able to find out the ins and outs, we're supposed to produce the perfect impression. This is actually not true about this particular paper. This particular paper, we can use some textual analysis to see, to find out which parts of the paper are earlier and which ones are later. Because they use this very different kind of language. In particular, we can treat it almost like a medieval document, a medieval text, and see insertions from different periods, only that in this development of quantum theory, the changes of language comes every 3 months, and as it goes, because the things develop so quickly that a very big change in language, how people write, happens in every 3 or 4 months. And for Dirac, the most important change of language came within the transformation theory. After which he changes the way how he writes his papers. And it's clear when you look at this paper to see that a portion of it was actually designed before transformation theory, which means middle 1926. And that's precisely the portion about the second quantization. And if one go back to his papers there, one can see the actual physical reasons why he would want to try to quantize psi function, which after that he couldn't admit because they didn't deliver what he expected them to do. But insofar as he showed that this method proves or delivers the result of Bose ensemble, then that became the starting point for him to apply the whole thing to radiation, because once it is Bose ensemble, it's possible photons. So that's about second quantization. The quantization of electromagnetic waves a la Jordan is the method that Dirac likes the least, but it's also the most powerful one. It's the one which allows him to calculate the most, more than the others. And so he applies to it when he to derive certain numerical things that he cannot derive from 3 other methods. And the method that he likes the most is the one that essentially quantum mechanics of ensemble of photons. So in a more or less a direct quantum mechanical picture, you try to think of ensemble of Bose particle, think about photons, derive for them a wave equation with symmetrically. This is the one that appeals most to Dirac's ontological feeling at the time. So, but insofar towards quantum mechanics, this produces kind of the two things, shows how powerful the method of quantization of electromagnetic waves is, and introduces this new strange idea of second quantization that will be used. The next building blocks came from Jordan the next year, and Jordan jumped on the thing, and basically, I mean, it was in some sense his thing from 1925, and he jumps immediately and adds two more important things. He shows how one can use second quantization to produce not the Bose ensemble, but the Fermi statistics, and therefore how to apply this thing not to photons, but to material particles or to electrons. That's kind of one of his fundamental contributions in 1927, and in 1928, and overall he formulates the basic problem for what become known as quantized field, theory of quantized field. He basically says we can try to design the new theory, the one that would be different from quantum mechanics at this point, based on the concept of quantized waves. We can use it for radiation, we can use it quantized waves as a psi function, as a second quantization for the matter. Put them together, and this is how Jordan thinks that we can produce the kind of a new fundamental theory that will be different from quantum mechanics. And he thinks that this quantized wave thing, for him, I mean, I wouldn't agree with him on that point, is the solution to the wave-particle duality, question. And the last building block that would become known as QED comes with the famous Dirac electron, relativistic electron of 1988. I wouldn't comment much because it's a very well-known story. On the one hand, miraculous thing that essentially once Dirac published this paper, for 2 years, almost everybody who was doing something quantum sort of started applying Dirac's equation to whatever problem they were doing. I mean, like the entire community kind of started using it. So it opens, created so many more new problems for everybody who was doing in the field, and attracted the entire community for about 1.5 years. And in this sense, it was very successful. On the other hand, there was immediately some difficulties, and Dirac was the first one who to mention them. Difficulties with the negative energy states and transitions to them. And Dirac, again, he was the first one to point out to them. But on the whole, since Dirac theory sort of spin came out so miraculously with it, so many new problems could be solved. So the difficulties did not attract too much attention kind of immediately because there were so many possibilities to using it. But later they will they will get more attention. So this was the kind of the building blocks kind of as how people will think kind of we will construct the next theory after quantum mechanics. So the two people came together to actually do this in 1929 and 1930, Heisenberg and Pauli. And they did it in a very sort of pedantic, systematic way. So they used all these kind of previous approach by Jordan and Dirac, second quantization for matter, quantization of radiation for electromagnetic field, kind of a Bose and Fermi for both sides, and the general ontological model of quantized fields. Put it all together in a very sort of consistent thing, and Dirac selected, and even proved that the whole thing is relativistically invariant. So they did a perfect job, one could think. Yet the result, when they published their paper, was a feeling of very strong dissatisfaction, or a very strong feeling of dissatisfaction, which is sort of strange in some sense, because by modern standards, their paper was a success. So why immediately kind of people didn't like it? And my feeling is that it was sort of psychological. Like quantum mechanics was such a miraculous thing for that particular people and generation. Like when they were doing quantum mechanics the previous 2 years, many previous problems that seemed to be big problems canceled out or were solved out miraculously. This didn't happen in this case. In this case, Heisenberg and Pauli put together all these partial proposals that were in a consistent scheme, and the problems all remained. Kind of nothing has been solved in a certain sense, and some kind of the essential difficulty. So the miracle didn't happen. And that the fact that miracle didn't happen was already enough for them to raise alarm. And that happened even, I wouldn't say immediately, even prematurely. Before that first paper was published, Jordan was already calling the whole theory a failure. It happened, the Heisenberg and Pauli paper was published finished in March 1929, so it will take about 5 more months, maybe 4 more months to publish it. I have to check the actual publication. So before it actually was published, Jordan went to a conference in Kharkiv, Ukraine in May 1925 and gave a review of the whole thing of sort of, in some sense, it was his problem to do the quantized field theory, and he called it a failure. He basically has, the whole thing is a crisis, we have to start it over again. Sort of it runs into some fundamental difficulties that require for fundamentally new ideas, for something else, and he called it kind of a crisis. His paper was published, I mean, he made this statement before even Heisenberg-Pauli paper was published. His own review was published a year later, but since then, kind of the word of the crisis has been pronounced openly and officially, and the entire community got to review it. And a year later, sort of in spring 1930, the conference in Copenhagen, that's a photo from it, met together, and I'm sort of relying on a partially second-hand report of this, so a report that I read. The report that I use is not by the person who actually was there, but the person who knew the people who were there. And so it may be somewhat exaggerated. But according to that report, that's what happened in that field, on that occasion. Pauli gave a sort of like, again, a review of all the failings, all the difficulties of his own, in some sense, relativistic quantum theory. And at each mention of the failure, the audience will cheer. Somebody will shoot the gun, the toy gun there. Somebody will blow the trumpet. And the whole kind of community cheerfully declare that kind of it's all garbage, roughly. So we have to kind of find something else. The theory doesn't work. So this is kind of, in some sense, something strange that we see kind of the people who are actually responsible for the whole field joyfully declaring that the whole field, which has just been started, I mean, it's not that it was there a long time, and it is in the crisis, and they have to start it over again. And the crisis they construed here was different from, I would say, the crisis, how the so-called crisis of the old quantum theory was construed. The crisis of the old quantum theory was construed post factum. So after the quantum mechanics sort of started, people looked back and said, oh yes, we had that many kind of difficulties. But if you look at how these people spoke about them in 22, 23, you'll find out, yes, some people thought there were difficulties, some other people, everything is all right, will be sorted out. So some were more positive, some were less positive. But even though who were critical, they would sort of, they will criticize privately, to maybe in correspondence, but there was no official open statement like our field is in crisis. In this case, it's different. In this sense, it's almost like an official verdict of the most important members of the community that the field is in a crisis, and we need a new revolution. In some sense, and I can't say we need a new fundamental ideas. We need to revise our concept in a very, very fundamental way. And another thing which is strange is that, so on this point, it looks like here I'm starting kind of playing my game that almost like the Kuhnian concept of the crisis. Because in the Kuhnian concept, there were like periods of normal science, then there was an extended period where the community loses confidence in their kind of fundamental ideas and fundamental concepts, and they go in all different directions. So that seemed to be kind of what happened to them, except that they didn't, QED even didn't have a normal stage. I mean, it was so short. I mean, it was just kind of, I mean, they didn't have the stage of the normal sort of a development. Kind of almost immediately once one completed, they declare, the community seemed to declare that we're in a state of crisis. We need to look to search out to search out for something else. So what were the difficulties? Some of the difficulties were real. It's just kind of think that the panic was premature, and some of the difficulties will be sorted out by different ways, not necessarily a radical one. There were, as I said, admitted difficulties of the Dirac electron, the reality of the negative energy state, one part. And there were some difficulties in how to quantize the electromagnetic field, not the radiation part, but the entire field, so to make sure that it's gauge invariant, and other things sort of later proved out to be mathematical difficulties, but nothing of serious importance. There were what proved to be kind of a much longer problem is there were infinite results popping up in different calculations. Most important at that stage, I think as far as I understand the formula is Heisenberg actually presenting on his and Pauli's theory. The most important for them at that point was that self-energy of electron was infinite, and they didn't know how to solve it. And they thought that the problem was much more serious than in the classical theory, but then the infinities still kind of were increasing and increasing in numbers. There were more and more of the kind. And the last group of the problem was the problem when, at that point, they all thought that electrons are within the nuclei. The neutron was not there yet. And if electrons were in the nuclei, they had to be relativistic electrons. And then there were kind of all sorts of problems with the beta decay, with the possible non-conservation of energy, and with strange statistics of the nuclei. So all these, in some sense, kind of were summed together and seemed to produce the impression that QED, or relativistic quantum theory, is in a big crisis. And what they wanted, in some sense, to replicate their previous success with quantum mechanics. So once again, revise the concept, once again, abandon something, find some kind of something fundamentally kind of different, and do some other steps. On this part, in this part again, kind of it seemed like Kuhnian notion would apply, basically saying that all different actors in this game gave some kind of different ideas of what can be saved, what can be revised, what part of the theory we can retain, what needs to be changed. And there's all complete disagreements about that. Like Pauli, for example, at some point thought, in his basic review of the wave theory, was that the portion he thought were relatively reliable were Dirac electron and Dirac's quantization of radiation. Everything else he was willing to discard, including segment quantization, including quantum field approach. But Pauli thought that the new fundamental ideas would explain the fine structure constant and explain the quantization of the electromagnetic charge. Other people went kind of different ways. Kind of Jordan will at some point will try to make a new, instead of non-commutational algebras, he tried to kind of make it more mathematical radical thing to do the non-associative algebras. Some people tried, instead of quantized wave, more corpuscle approach. Some of these approaches reproduce the same thing, just kind of a more or less equivalent. Some people were trying to speculate that if we're failing, then we need to analyze what's observable, what is not, and once again, get rid of unobservables. And again, with a lot of disagreement. Bohr, for a while, thought that it's electron spin which is unobservable. And he was not the only one. Landau and Piles at some point published a paper claiming that electromagnetic field is unobservable and therefore cannot be used as a notion field. So, and this is the point how caricature is showing how Bohr disagreed with their point, because sort of different actors tried to say they were ready to sacrifice some things and retaining others, and there was no agreement. And even at the kind of latest point, Dirac also even tried non-conservation of energy as late as 1936, and he tried to do something about it. And in the end, he wrote a letter basically saying, "Oh well, you cannot do revolution every time you want it." So roughly, kind of, it didn't want it, so admit it. So in the end, the whole thing came to, in some sense, almost nothing. A revolution didn't happen. Now, why I use the Trotsky's concept of the permanent revolution here? I think it makes a perfect analogy. I'm not claiming that these people followed Trotsky's prescription or were influenced by his ideas. Some of them actually could have. I mean, Trotsky's views were relatively well known, so some of them possibly knew of it, but I didn't see any evidence of that. Why using this data, it helps to explain what was going on. Trotsky's concept of the permanent revolution was essentially a word to explain the revolution that came prematurely. Revolution happening in Russia, in the country where, according to the classical Marxist theory, the economy was not ready for socialist revolution. The economy was ready for capitalist revolution, but not for socialist. Yet, on the political level, most of the population voted socialist parties. So there was a political precondition. So socialist parties could actually get in power, but there was no economic basis for that. So something contradictory to the Marxists. So in order to sort of, in some sense, save the appearances, Trotsky designed his concept of the permanent revolution, saying that we can start with the capitalist revolution according to the classical Marxist theory, and then kind of with the party in power, develop the conditions kind of in order to proceed to socialists. So this is the concept developed to the problem: how do we try to do revolution in the state where there's no yet conditions for it? The thing is prematurely, and this I think is a more or less diagnosis of what those kind of quantum theorists were trying to do with the relativistic quantum theory. That they were too ready to declare their field a failure, possibly because they were under the influence of their great success with quantum mechanics. I mean, their radicalism played out so nicely in quantum mechanics and so much rewarding that they wanted to some kind of reproduce it, kind of once again, kind of to do the next revolution, kind of the next one. So after the successful capitalist revolution, they wanted a socialist revolution in the new quantum theory. Now, 5 more minutes or 3 more minutes? 6. Oh, okay. I'll have time for questions. Now, how the whole thing got resolved? Anticipating Alexei's talk, next one, I'd say the crisis was not resolved, but it withered away gradually. The expected radical evolution didn't happen. Most of the proposals that came out from these great minds of quantum mechanics did not deliver the expected radical revision of foundations. In some of the approaches, I said, they just reproduce the same difficulties and the same result as with other approach. They prove they're roughly equivalent. How the things, but gradually the acute feeling of the crisis became sort of like, felt, I would say, less and less acute. The main method how it was doing so was not by some big radical revision, but by a different route. And not that they wanted it, but that's how it happened. The community started increasing the number of so-called elementary particles. And each new elementary particles brought its own problems with it. But and it was not the radical solution that kind of people wanted, but each of these kind of new elementary particles discovered solved some of the previous problems that existed. So when neutrino and neutron were introduced, it resolved most of the problems about supposed electrons within the nuclei. There were no more problems with statistics and nuclei. One did not have to think that electrons and nuclei are relativistic, so all these kind of supposed difficulties could be resolved or written down. They were no longer there. When positron was discovered in 1932, so again, it triumphantly turned a supposed difficulty into a triumph. Again, not that everything was resolved again, but kind of there was no longer such a big thing with the negative energy state. There were still many people who didn't buy Dirac's whole theory, but the sort of the very acute feeling of crisis at this level sort of kind of dissipated. Fermi resolved some of the problems, mathematical problems with quantization of the electromagnetic field. He did it in 1930, but his first paper was in Italian, so only the English review of 1932 got really noticed. So in essence, it's not exactly the revolution that was supposed to happen, but with unexpected discovery of new elementary particles, some of, not all of the problems, but some of the problems sort of were no longer seen as fundamental or as damaging as the early one. The one thing that really remains was the infinities, the divergences. And they seem to be kind of worse and worse with each next steps, because the number of them kind of multiplied and they create. And that was a sticking that never got kind of fully resolved, but that was not enough to sort of to justify kind of again the feeling that this is when you need kind of the next revolution. I said it withers away, no reaction revolution happened, and radical proposals didn't work. So what happened to the people who produced them? To some degree, I would say they resigned to that lesson that I said Dirac formulated. I mean, you cannot produce a revolution every time you want it. Sometimes you have to wait, but it doesn't mean that they became satisfied. If you look at this generation of people from Pauli and Heisenberg and Landau and Dirac, you notice that all the way through, they still basically until they're still alive, they're still hoping that something more fundamental will come. So even when QED, like in late 1940s, sort of resolved most of the calculation difficulties, in a relatively conservative manner, people like Dirac would not say this, but they saw that it's like a kind of formal trick, but not the actual fundamental. So in some sense, they no longer, they don't always continue sort of striving for some radical proposals, but they remain hopeful. Or in some sense dissatisfied, sort of. They hope, and more or less for as long as they were alive, and they hope that something more kind of a fundamental kind of will come there, and they would not fully buy the QED of Feynman and the group and of that generation. And now kind of the last thing and the last slide, kind of what Kuhn has to do with that. When I was kind of looking at this story and this episode, I first thought, like if we take this Kuhnian model, many historians all over decades were trying to see which stories from history sort of fits the Kuhnian model, where the revolution happened. A revolution kind of is often talked to. There's much less frequently talk about the crisis. So I would say that there were not many occasions in history of science when we see the community of scientists behaving like Kuhn thought they would behave in what he thought the crisis stage, where the community would acknowledge our field of science is in shambles. We don't deserve any grants. we don't know how to do our work. So that essentially, it's an open admission of failure. I would claim that first I thought it happens rarely. I mean, not like Kuhn thought that it would be kind of the standard thing. Somewhat later I thought maybe that was the only case that actually fits the Kuhnian concept of the crisis. Sort of the only one that I know in history where the leaders of the community would openly, for extended period of time, would basically say, kind of, we don't believe our own foundations. We all kind of need to look for something else. And at some later stage when I kept thinking about that, I thought, well, maybe actually the connection is reversed. It's not that that's the only case that fits the Kuhnian model, but maybe Kuhn get his ideas about crisis from knowing that case. But in order, so I cannot prove that, but kind of why I think that maybe kind of there may be something in this suggestion is that Kuhn, we need to go back to Kuhn not as Kuhn as historian, not to Kuhn as philosopher, but to Kuhn as a physicist. Kuhn as a graduate student in physics in late 1940s, who got in sort of a socialized indoctrinated into the quantum theory of radiation with his advisor Van Vleck. And here I probably may need Michel's help because I have no idea what Van Vleck thought on the issues of crisis and thing. So on the one hand, Van Vleck belonged to that generation, kind of that knew about the crisis, that sort of lived through it. I don't know what his particular view on that, but I kind of suspect that Van Vleck may be the one who could have, in some sense, communicated this idea, because in late 1940s, it was still kind of in the memory of the generation. Maybe the crisis was not something that was often talked to, as often as it was in the mid-1930s, but certainly it was talked very often in Van Vleck's sort of early days. And so my suggestion now that maybe Kuhn could have kind of, because he was trying to start a career as a quantum theorist in the quantum theory of radiation and the Specter with Van Vleck as his doctoral advisor. So kind of, and he must have learned something about his own field, or quasi-history, so to say, or folklore history of that. And if that is true, then Van Vleck possibly communicated to him kind of the idea, or the vision of that, the previous generation of the older generation of the leaders of QED. And in this sense, kind of, I suspect that maybe Kuhn, kind of, a certain portion of Kuhnian model of in philosophy of science, kind of could have come from that kind of experience of that particular generation of physics. Thank you.
Yeah, I have a comment and a question. First, on the Dirac quote with you can't always have a revolution when you want to. It should be noted, of course, that that was in response to experimental results, which then turned out to be not reproducible.
So, he first thought there was experiments that suggest non-conservation of energy and tried to do a theory.
Right.
And then experiments showed out to be kind of inconclusive, and then he retreated.
Yeah, so I mean, that kind of, it's not just people trying theories and they don't work and say. But the other question I have is, you seem to be implying, by the way you presented, and maybe that's not what you mean to say, that this spirit of permanent revolution in somehow inhibited progress in this period, or kept people from seeing the less radical solution to the problem. If that's not what's I mean, that's just what I got from the gist of your presentation, like from the tone of your presentation.
No,
so I was wondering
I wouldn't use the word
inhibited.
I wouldn't use the word inhibited, but I would say that, let's say, in some other situations like that, people would not behave in such a panicking way. They would basically admit, yes, we have problems, but we will solve them, or they will sort out eventually. So it's a different way how people react to real existing problems, and the way how they do it kind of may depend on the period of time they live, their previous experience. I think I don't know. There was some kind of like necessary kind of progress there, and they didn't buy the progress when it actually came. In your definition of that, they didn't buy the renormalization as a final answer to the thing. But I do think there was something strange or specific about that particular generation that lived through the quantum revolution, that made them want to reproduce another one as quickly as possible in some sense. And which, without that experience, probably, let's say, physicists nowadays would not be producing such a discourse. Simply would not.
So first, to answer your question to me, I think the famous statue line applies like a beautiful theory killed by an ugly fact. So it's very tempting to think that that this is where Kuhn's notion of crisis comes from. And I myself thought for a long time that the one example where it seems to work is like in the crisis leading up to the quantum revolution of 1925. But I actually don't think that's the case. I mean, of course we can't ask Kuhn, but for instance, I did ask Anderson, who took his degree with Van Vleck at the exact same time, and Van Vleck told him nothing about like the history of physics. Van Vleck, of course, also, as you know, is not working in QED at all. He's a solid-state physicist. And then, like, I think the most important stuff is, like, on the Kuhn centenary, like the 50 years of the structure, right? So there's these papers by Hofbauer and Joel Isaac, like tracing sort of the intellectual development of Kuhn, and it seems that they can sort of account for these things, and then you have like structure in '62, and it's only after that, right, that Kuhn gets involved with the Archive for History of Quantum Physics through Van Vleck. So my sense is that this is not the source of the notion of crisis. Now, yeah. So one other question, like a small point, and that is that you said that Jordan like started to really doubt like his own program, like in this talk that he gave at Kharkov in the Ukraine. And now, so I'm looking at it with a bit of tunnel vision, looking at his confidence in these calculations on black body fluctuation, right, that we just heard about. And on that particular point, that is probably the most confident statement that we have of Jordan, that this is exactly right. He had doubted it a little bit before in discussion with Smekal in 26, but I just looked it up in our paper, and in Kharkov, he is extremely confident that we have forever solved the problem of the wave particle duality. So I was surprised by that.
Okay, so first, indeed, kind of, I don't see any of this kind of a Kuhnian thing in his work on the archives, in his interviews. So that's why I suggested that kind of I don't insist on that Kuhn might have gotten some inkling of what kind of that the crisis may exist, not from his experience as a historian, but from his experience as a graduate student in physics like that. But remaining, since the evidence is not there, kind of let's leave it as it is. Not impossible either. So Schwinger was around, yes. He was kind of the other possibility than Van Vleck. But to the second point, I think I can say something definite. So all of these kind of guys, kind of once they started talking about the crisis, each of them in some sense selected some part of the thing that they believed in and some other part that they didn't believe in. They all kind of in some sense agreed that the whole thing doesn't work, but certain elements could. And which exactly elements they select, it varies from one. So Jordan could have still continued to believe that he solved that problem once and forever, and at the same time talking about kind of the crisis of the Pauli-Heisenberg thing.
My question is more about your last slide on historiography. First, you know there is a kind of a predecessor of somebody who went in the same direction, trying to say that Kuhn's ideas came from his experience or from his training or from his immersion in the culture of physics. It was Marabella in his book Quantum Dialogue. She did not speak explicitly about crisis, but the notion of paradigm. Paradigms.
The notion of what?
Paradigm. So my question is, do you have any comment about any kind of relation between the considerations you are doing and what Marabella said? And the second question, it's not exactly a question, it's a comment. I am very sympathetic to your statement because I have tried Kuhn was one of the few philosophers from that generation who became philosophers or entered in the field in the 50s, 60s, and so on, who did not have any sensitivity to the foundational issues in quantum mechanics, even when this debate was revived in the 50s, 60s, 70s. So when he died, Bell theorem and so on was on the hand. And as far as I know, I did not find one single word of Kuhn toward this subject. Then my guess is that he was indeed very committed he had a strong commitment to the orthodox presentation of quantum mechanics, and this only come from his experience, early experience as physicist.
As kind of far as Marabella goes, I'm sympathetic with her work. Yet, insofar as she uses the concept of crisis, it's more often, as I said, when people when a quote-unquote revolution happens, when people go back and retroactively say there was a crisis. And in part of this is partially what Marabella does in many things. What I try to make a distinction between these things. So we can debate, for example, was a crisis in quantum theory in 22, 23? It was not the word actually used by the participants back then, but retroactively, post factum, it could be ascribed, and then we can decide on what are the criteria and so on and so forth. And in my case, it's kind of the word of the talk about crisis massively used by the participants themselves at that particular time. And I try to kind of to make the distinction that this is what I'm after. Not about, sorry, how do we define the crisis, was the actual crisis, but whether people talk about it or don't talk about it, right at the time, right of those who are using that. And as far as kind of, I agree with you that Kuhn, I don't know if also any of his interest in interpretational things on quantum mechanics. I don't think that we should immediately conclude from that he was an orthodox believer. There were, and not that I'm claiming that, but another possibility would be quite common among the American physicists is sort of the attitude towards like shut up and calculate, roughly. I mean, interpretational issues is something that Europeans are concerned with, and up to a point that kind of worked for many. So they were not kind of the most fair. So I'm not saying that that's what could be lead, but it could have been done. So basically, from his silence, we cannot necessarily derive kind of exactly, unless we know something kind of more about him.
Okay, 2 more questions, one from Mariana, and then Chris.
Thank you very much. I really I agree with you. I would like you to specify a bit more this scientific community, because you spoke about this generation, but some, I don't know, Wigner, von Neumann, Fermi, I don't really see them. So what other elements?
Indeed, what should I say, the talk was mostly by people who were sort of like part of those people who went to Copenhagen, so visiting. A little bit wider than that. Like Fermi was relatively immune to that. Fermi didn't use that. And his solution was, or his attitude was rather, let's things sort out, and kind of a great sort. That's true. I mean, I'm not saying that everyone was kind of on the same background, but it was massive enough. And the center of the community was sort of basically the key authors of the whole thing were there.
Well, so basically you're doing the Paul Foreman here, right? You're saying that all these guys were like reveling in the crisis, that they didn't have any rational grounds to see.
That's what I would like to say. If you or me ever had in our academic life something like a discovery of quantum mechanics, we would forever want to do something like this again. And in some sense, because enjoying such a great thing, I mean, once you always want to replicate it. That's what I'm saying.
But I mean, what you are implying is that there was no rational grounds for declaring a crisis.
No, there were real difficulties. But the panic around them was somewhat exaggerated. Especially at this very early stage. I mean, the normal attitude would be, the theory was very new and thing.
Well, a theory that only gives you infinite results is
sure, but one thing is kind of to wait and see what can be sorted out, what cannot be sorted out. I mean, it was. I would say that yes, it was a little bit premature to declare the whole thing dead. Yeah.
Okay, can we make it short? Yeah, so would you claim that the way that they look for that was a question of rhetoric of crisis is something which is clearly different here, or was it more than the rhetoric but also the kind of solution they looked for?
Oh yeah, they looked for radical solutions. Yeah. So I mean, it was rhetoric, but they believed in it. Yeah. Sure.
So they practically looked for.
Yeah. Yeah.